So let's go through an example. Here we're going to assume that the variances are known and they're equal. Sigma A equals sigma B, which is 15. We are going to conduct a one-tailed hypothesis test to determine if there is a significant difference in the breaking strength of the two composite materials. And we're going to use an alpha of 0.05. The hypothesis test that we're going to be performing is an upward-tailed test because we've calculated an average for A to be about 482 and that of composite B to be 464. Based upon your sample averages, there's no way that you would hypothesize that the strength of A is less than the strength of B. And so oftentimes if you've got the data, your data points to if you're going to do an upper-tailed test or a lower-tailed test. So let's go ahead and do this in Excel. I've got this in a file called hockey sticks. I've already named a bunch of things and I've calculated statistics. So this is X bar A, X bar B, sigma A, and sigma B. And actually I need to put this back to 15. NA and NB. I've also got our alpha value and that's named alpha. To perform the hypothesis test, we first need to calculate a test statistic. Here on the left up here, we have the test statistic for when variances are equal. I can simply type in this formula, X bar A, so A here is analogous to population 1, minus X bar B, dividing by sigma A, and it doesn't matter if I use sigma A or sigma B here because they're exactly the same. And then I'm also dividing by the square root of 1 divided by NA plus 1 divided by NB. And when we do that, we're getting a test statistic of 2.59. Now remember, for an upper-tailed test, and that's what we're doing here because we're proposing that mu1 is greater than mu2 as our alternate hypothesis. In order for us to accept the alternate hypothesis, we have to show that z0 is greater than z alpha. So I'm going to calculate a z alpha. The z alpha is simply the z value that has alpha percent or area to the right of it. We can do the norm.s.inv. Remember that this is a cumulative or left-tailed function, so I have to do 1 minus alpha. And that means that our z value that has 5% of the distribution to the right is 1.644. Our conclusion is that we would accept the alternate hypothesis because our test statistic is way out in the tail. It's beyond our critical z alpha value of 1.645. And so our conclusion is accept the alternate hypothesis. Composite A really is stronger than composite B, and that would be our conclusion based upon these numbers and assuming that we knew the population standard deviations. Real quick, I wanted to show you a tool that's built into Excel. We can go up here to the Data tab, Data Analysis, and there's at the very bottom there's a z-test 2 sample for means. You can click on that. It brings up this tool, and here we can put in our variable 1 range. That's just my composite A. Variable 2 would be my composite B. The hypothesized mean difference, oftentimes that'll be 0. Variable 1 variance. We know that the standard deviation is 15, so I can type in 225. The variances are equal for this case, so I can also put in 225. And I'm going to put in an alpha of 0.05, and I'm just going to output this to my spreadsheet here. And when I press enter, it actually will go through and it's going to calculate a lot of the same things. We have our observations, hypothesized mean difference, and if you look at this, it's performing a one-tailed test and a two-tailed test. This tool always performs a lower-tailed test, and so it's actually swapping those two, and we get the same exact z value for our test statistic. We also get a p-value here. We get the critical 1.645, that's what I calculated up here, and it also performs a two-tailed test. Just real quick, let's calculate a p-value. A p-value is always the area to the right or left, depending upon if you do an upper-tailed or lower-tailed test of your test statistic. We can simply do the norm.s.dist function on our test statistic, z0, cumulative, and we also have to subtract that from 1 for an upper-tailed test, and we get the p-value is 0.00473, which is what that 2 sample for means test did when we used the data analysis tool. Now let's look at a slightly different scenario. The variances of the two populations are unequal but known, so we know that sigma A is 10 this time instead of 15. We're going to do the same thing. We're going to perform an upper tailed test, and we're going to see what our conclusion is. So I'm going to just modify this. I'm going to change my standard deviation that's known. Composite A is 10. We have to use a slightly different test statistic because now our variances are unequal. So I'm going to use this equation over here on the right. And so I can just modify this from earlier. We're going to, in the denominator, have square root of sigma A squared divided by NA plus sigma B squared divided by NB. And when we do that, we're getting a test statistic of just under 3. We have the same critical Z alpha, 1.645. I can calculate my p-value. It's done in the same way. We're getting approximately the same p-value. And if you want, you can always run this data analysis tool. In this case, we're going to have to change our variable 1 variance. Instead of 225, it's going to be 100, right? Because the standard deviation is 10. And I'm going to run through this the exact same way. It's calculating a test statistic of exactly what I got, as well as the p-value for the one-tailed test. Again, this always calculates a two-tailed test as well. So hopefully you learned a little bit more about comparison of means when variances are known in this screencast. In the next screencast, we'll talk about the situation when variance is unknown. Thanks for watching.